the verifier has no time to do it on its own. And what the subject protocol would do is to strip those summations one by one. So I'll show how we strip the first summation, and all the others will be stripped in the same way. So we start by defining the following function. And g of alpha is equal to the sum here starting from x2, where x1 is assigned the value alpha in the field. Now, because p sub phi is a low-degree polynomial, in particular g is a univariate low-degree polynomial. And now the protocol goes like that. So we have the verifier and the prover. And the prover starts by sending a function g bar, where g bar is supposed to be equal to g. The prover may send a true g, but it may also lie. Okay, so this is one possibility. Oh, actually, we shouldn't. No, we can't because the field is very large. Yeah, we send the coefficients of the low-degree polynomial.
How large is the field? Are you getting to be exponentially large or polynomial?
We can do both. Actually, in this case, sorry, the field needs to be exponentially large. In this case, later we will be able to get rid of this restriction, but the field is exponentially large. Sorry. Yeah. Yeah, we can do all kinds of tricks, and we will do later. And the field will be exponentially large, but g is supposed to be a low-degree polynomial, so the prover just sends some low-degree polynomial g bar. And the verifier, okay, so the first thing that the verifier checks is that g bar of 0 plus g bar of 1 is equal to 0. And if the prover was telling the truth, if g bar is indeed equal to g, then after we made this check, we are done. It means that this sum is indeed 0. So now all that remains is to check that g bar is indeed equal to g. And to this end, the verifier sends a random value r in the field. And now the prover is supposed to prove that g bar on r equals g on r. In other words, the prover is supposed to prove that this sum x2 goes from 0 to 1 xn 0 to 1 p sub phi. Oh, sorry, let's call this random value r1. And the prover is supposed to prove that this is now equal to some value v1, which is g bar r1. In other words, the verifier computes g bar at r1 and asks the prover to prove that this equality holds. And now we have reached a claim of the same form we had before, sum exponential, sum equals some value, but we stripped the first summation. And the point is that this new claim has two properties. First, completeness. If the first claim was true, this claim will be true. If the first claim was false, this claim will be false with high probability. And the reason is that those are two low-degree polynomials, and therefore they intersect at very few points. And now we can repeat this process, stripping the summations one by one, until eventually we reach an expression of the following form: P sub phi R1 to Rn equals some value v. And once we got to this expression, this is something that the verifier can compute on its own. It doesn't need a prover for it, so the verifier will simply compute this expression and check that it's indeed equal to v. And at this point we are done. If phi was unsatisfiable, this claim will hold, and if phi was satisfiable, this claim will be false with high probability. So the verifier will catch the prover. Okay, we are on time. Okay, so this was the original proof of QNP contained in IP. Now let's go to the preliminaries. Maybe let's put some V's here. Okay, so we finished the introduction, and we showed the original proof of QNP contained in IP. And now let's do some preliminaries. So first of all, we are talking in this talk we are only talking about linear error correcting codes, which we will usually denote by a function c from f to the k, a linear function c from f to the k to f to the l. Now the images of this function are called code words, and they have the property that each two distinct code words of C differ on delta fraction of coordinates, of their coordinates, also, we will use, I should say, we use this notation to denote that some string in f to the l is a code word of C. And also note that the all zeros string is a code word of C. Or actually, the all zeros message is mapped to the all zeros code word. And this means that all the non-zero code words are non-zero on many of their coordinates. Delta would be some high fraction, large fraction. In this talk, delta will usually be at least 1 over polynomial in n. In the previous proof, we actually had here exponential. So for the rest of the talk, 1 minus 1 over polynomial would be sufficient. And without loss of generality, we can assume C is systematic. which means that the first k coordinates of the string of the code word are always equal to the original message. And this can be done by a suitable change of basis. Okay, so next thing I want to do is the. Oh, okay. This was standard. Now I'm going to define some non-standard notation. Or maybe I'll write it there. It will be more time. First, I'm going to use the following non-standard notation and denote by n in square brackets the numbers from 0 to n minus 1. Usually we use to denote numbers from 1 to n, but this will be more convenient. Second, when we talk about codes, rather than viewing messages and code words as strings, it will be more convenient to view them as functions. So we have, say, a message x, which is a function from these coordinates to the field f. Oh, sorry. Oh, no. A second.
The message is in f to the k, and it maps to strings of size L.
No, this just says that the message is in f to the k.
Instead, the x was used to be viewed as a string in f to the k. Now, instead of viewing it as a okay, instead of viewing it as a string, I view it as a function, and the code word will be viewed as a function c from L to f.
What is f here?
F is a finite field. Okay. Now, a particularly useful code would be what I will call for this talk the low-degree extension code. Usually, low-degree extension is used in a few kinds of meanings, but I would want in this talk to define it as a particular code. So we fix some finite field A. So we fix f and some set age contained in f. Messages of LDE code, low degree extension code, are viewed as functions f from age to the n to f, and LDE code encodes f to f tilde, what's called the low degree extension of f, which is the unique low degree polynomial from f to the n to f, from the field f to the n to the field f, such that the individual degree of f tilde is at most size of h minus 1. There is a unique such polynomial, and we will encode the polynomial to it. If you would like, this LDE code is a systematic version of Reed-Muller code. The individual degree is the maximal degree of a single variable in the polynomial. So every variable in f tilde has degree at most h minus 1. Okay, and again we call f tilde the low degree extension of f. Now what can we erase? We'll erase this.
So once you choose the subset H,
Sorry?
once you choose the subset H, the extension is uniquely defined.
Right. Once we
There's only one linear.
exactly. Once we choose the set H, the low degree extension is uniquely defined.
Degree is at most h minus 1. You mean degree in each variable?
Right, individual degree. Okay, so the last thing I want to say in the preliminaries part is to define the notion of tensor product codes, which will be a key concept in this talk. So the tensor product is a classical operation on codes, and we can view it as generalizing the move from univariate polynomials to multivariate polynomials. In particular, if we take a univariate LDE code, say of degree d, and we take its tensor product of order m, then we get an m-variate LDE code. So for start, let's define the tensor product of order 2. So let's fix some code C from f to the k to f to the l. And C to the tensor product of order 2 is a code that maps messages in k squared of length k squared to messages to code words of length L squared. And instead of defining the encoding, for our purposes, it will be sufficient to define the code words. So a code word of C squared is an L by L matrix such that all the rows of M are code words of C, and same goes for the columns. This is the definition. It can be shown that the dimension of the space of those matrices is indeed k squared, and furthermore, the distance of c squared is delta squared, assuming that delta is the distance of c. Now, a special case of this tensor product of order 2 is bivariate polynomials. So it can be shown that a function p is a bivariate polynomial p of xy is a bivariate polynomial of, say, degree d in every variable, deg p of x is at most d, deg p y most d. This is true if and only if p of alpha for every fixed alpha is a univariate polynomial of degree at most d, and p with y fixed to alpha is a low degree polynomial is a polynomial of degree at most d. So this is a special case of this tensor product construction. In general, let's define general tensor product. So c to the n maps messages of length k to the n to code words of length f to the n, and has distance delta to the n. Oh, sorry. Oh, right, sorry. L to the n. And we would like to view code words as functions from the hypercube L to the n to f, such that for every vector of coordinates, call it I bar, of L to the n, and t that goes from 1 to n, it holds that c I1 to I t minus 1 that is, we fix all the coordinates except for the tth one, this is required to be a code word of C. If this is true for every tuple of coordinates I and every t, then C is a code word of C to the n. Small c is a code word of capital C to the n. And it's an if and only if. This is the definition of the code. And again, it can be verified that the n-variate low-degree extension code is indeed the nth tensor product of the univariate low-degree extension code. Oh, now we can define one more special notation. So say we have some code word C of some code C to the n, and a Boolean formula phi from 0, 1 to the n to 0, 1. We'll say that small c is consistent with phi if they agree on the hypercube. That is, for every I bar that belongs to 0, 1 to the n, that is, they agree on the Boolean hypercube, it holds that C I bar equals to phi of I bar. Phi of I bar is defined because I bar belongs to 0, 1 to the n. And this is, again, I mean, it's a simple definition, but it will also be a key concept in this talk. Okay, this concludes the preliminaries. So now for a more philosophical part, reflecting on QNP containing IP. So let's look again on the proof of QNP containing IP. What we want to do there is to prove that some formula phi is unsatisfiable. Now, what is the difficulty here? Well, there are a few difficulties, but one difficulty is that the verifier, which runs in probabilistic polynomial time, needs to be able to distinguish between formulas that have a unique satisfying assignment and formulas that are unsatisfiable. And if we look on those formulas as strings, we look at their truth tables as strings, it means that the verifier needs to be able to distinguish a string, two strings of length 2 to the n that differ only at one point. And obviously, this is difficult to do because of the needle in the high stack problem, at least in polynomial time. But as a thought experiment, let's observe that this task would have been easy if the verifier was allowed not only access to the truth table of the formula, but also to its error-correcting encoding via some linear code of the truth table. Why? Because, well, we know that in linear codes, the encoding of the all zero string is the all zeros code word. So the encoding of an unsatisfiable formula would be all zeros. And on the other hand, if every non-zero code word has a lot of non-zero entries, so the verifier could just choose a random entry and check whether it is 0 or non-zero. And in this, at this point, the verifier would be done. So if the verifier could, in general, get access to an error-correcting encoding of any Boolean formula, this would actually prove that QNP is contained in RP. Or actually, yeah, in RP. So now let's ask, okay, in this argument is kind of the intuition I mentioned before for why low-degree polynomials come up in this proof, why do we have arithmetization here. So let's ask, is this what arithmetization doing? So we get, so the arithmetization gives us this polynomial p sub phi, which is, it is a code word of the low-degree extension code. And moreover, it is efficiently computable, so the verifier can access its entries in polynomial time. But unfortunately, p sub phi is not the encoding of the truth table of phi. Well, one way to look at it is to note that the messages of p sub phi as of the code that p sub phi belongs to are of length are of a larger length, but an easier way to see it is just to see what's the arithmetization of the formula x and not x. So the arithmetization of this formula is the polynomial x times 1 minus x. Now, this polynomial is a non-zero polynomial. It is non-zero on some of the entries. But on the other hand, the correct encoding via the low-degree extension code of x and not x is the zero polynomial, because the truth table is the all-zero string, so we need to map it to the all-zero code word. So arithmetization does not give us an encoding of the formula. Or it does not give us an encoding of the truth table of the formula. For the rest of the talk, I'll just say an encoding of the formula to mean the truth table of the formula. So what does arithmetization does give us? Well, arithmetization gives us a polynomial, p sub phi, which is consistent with the formula. And I would like to claim that this is the key important property of arithmetization, the fact that it is consistent with the formula. So now, as part of this reflection, let's note that we have two interesting polynomials in our discussion. The first is the low-degree extension of the truth table of phi. Let's denote it by phi tilde. And this is an encoding of the truth table. But the problem is that it is not efficiently computable. Unless NP is contained in, or co-NP is contained in RP. Sorry? Phi is a Boolean formula, but this is phi tilde. Sorry. And the second polynomial is p sub phi, which is a code word and is efficiently computable. But all we can say is that it is consistent with. And the point I would like to make is that what the sum-check protocol really does, or what it can be used to do, is to build a bridge between those two polynomials. What the sum-check protocol really allows us to do is to evaluate this polynomial when we can only access this polynomial. And more generally, what we will see is that we can replace phi tilde with any code word of any tensor code that encodes the truth table of phi via any tensor code, not necessarily the low-degree extension code. And we can replace p sub phi with any code word of some tensor code that is consistent with phi and is efficiently computable. Yeah?
In the original, you're viewing same LDE code?
No, they are not in the same LD code. In particular, P sub phi will have higher degree than phi tilde. Phi tilde will have individual degree 2, and P sub phi will have some polynomial degree.
But you could say you can just fix some to the upper bound and view them as both lying in that same code. Is that useful, or?
No, I don't think it's useful. At least I don't see any use to it. Yeah.
So, was it essential for the code to be linear?
Yeah, it will be essential for us. And okay, so in the proof so far, we implicitly used it in a few places. First, we used it in the arithmetization when we used it, for example, here and here. And we also used it here in the summation in order to make sense of this summation. And it will be useful for us in the general proof. Sorry? Yeah, phi tilde is actually multilinear. So what? So the plan for the rest of the proof is the following. First, we'll prove formally what I just said, that in general, the sum check protocol can always serve as a bridge between an encoding of the truth table of the formula via some tensor code and any code word that is consistent with the formula of some other tensor code. Then, and this is what I call the revisiting the sum check protocol. In the second step, we will show that actually for more or less, or morally, for any tensor code, we can construct such a code word of the tensor code that is consistent with the formula. This is not exactly true, but a strong form of it is still true. Or a weaker form that is still strong of this claim is true. Okay, and then if we will have time, we will see how to take all these ideas that we only discussed so far in the context of coNP containing IP and lift them to IP equals PSPACE. Otherwise, we'll just see the proof of coNP containing IP. I think it will be a good time to take a break. Okay. So we finished with the reflection, and now let's revisit the sum check protocol. So I mentioned that the sum check protocol serves as a bridge between two code words. One is the encoding of the formula, and the other is consistent with the formula. Let's make what I'm saying more precise. So let's fix some formula from 0,1 to the n to 0,1. Let's fix some error correcting code C, which encodes messages of length 2 code words of some length. It's immaterial. We will also have some code D that has some code message length K and code word L and code word length L. And we will define the code word C to be the encoding via C to the n of the truth table of phi. Note that the message length of C is 2. So the message length of C to the n is 2 to the n. So you can indeed encode phi via the truth table of phi via C. We will also take some code word small d of the code capital D to the n, and that is consistent with the formula phi. Now, after fixing all this, what I claim is that there is a generalization of the sum check protocol that does the following. It takes as an input a claim C, small c at some coordinate I bar equals some value u, and it outputs a claim of the form D at some coordinate r bar equals some value v. And those claims satisfy the following properties. First, completeness. Input, if whenever the input is a true claim,
Claim is not about necessarily a coordinate, it's about the sum of coordinates.
no, it will be a coordinate.
It will be, but I mean, in the protocol you just gave the
I did not give yet this generalization.
I know, yeah, I'm just saying that
It's not the
way
sum.
to interpret the obvious.
Yeah, so I'm saying, no, it's not going to be a sum, it's going to be what I wrote. It's true, you are right, this is not exactly the subject protocol as I presented it before.
That was my only point.
Okay. So the completeness property will be that if the input claim is true, then the output claim is true. So yeah, for some, if the prover is honest, and in this case the prover has no incentive to cheat. And the soundness would say that if the input is false, then with high probability the output is false. Oh, maybe I should write it more. This is what I claim that the subject protocol can be made to do. And now, why should we care about it? Why is it useful? So for start, observe that we can choose the code word small c to be the low degree extension of the truth table of the formula. And we can choose small d to be the arithmetized version of the formula. And since we can compute, and this means that we can choose a random entry or any entry of the low degree extension of the truth table of the formula and use the subject protocol to translate this claim into a claim about the arithmetized version of the formula. And this claim is something that the verifier can check on its own because the arithmetized version is efficiently computable. So this essentially allows us to compute any entry of the low degree extension and in particular check that a random entry is 0, which is what we need. So now let's see how we can generalize the subject protocol in this way. Okay, so we start with this claim C, or both parties start with the claim C at coordinate I equals some value u. And my first point would be that they can rewrite this claim in an equivalent way as the following scary sum sigma I1, oh sorry, J1. 0, 1 times alpha 1 J1 times we have many summations like that until we have Jn equals 0, 1 alpha n Jn times phi J1 Jn equals u. Now, why they can do so? Why do we have this scary sum? Well, basically, and what I'm going to say is true for any code, not just tensor product codes. In any linear code, any coordinate of the code word is a linear combination of the coordinates of the message. This is the definition of linearity. What I am doing here is to express a coordinate of the code word, seed coordinate I, as a linear combination of the coordinates of the message. Now, in a general error correcting code, there is no reason that this linear combination will be of this particular form. But the point is that in tensor codes, it will be of this particular form. I'm not going to prove it, but it's a 2 paragraphs proof that's a bit technical, but it's very easy.
So why is this not the most general form?
The most general form would be to have a coefficient that depends on all the J1s, on all the J's. But the thing is that what tensor products do is essentially to encode every dimension via C separately. So we have, so actually those coefficients, those alphas, would come directly from the generating matrix of the code C. Or from that is, for example, the alpha ones would be the coefficients that come from, say, the I1th row of the generating matrix of C, and so on.
So here is the product is tensor product?
Sorry?
Is the product is tensor product with vectors?
No. Those are scalars. Scalars, yeah. Alpha 1 would be a vector, but alpha 1 J1 is a scalar. Okay, so now we have this claim, and the second, yeah.
What are these alphas efficiently computable?
Yeah, they are efficiently computable. They actually, I should have said it. You are right. The alphas are efficiently computable, and actually they are just they just come from the generating matrix of C. So, for example, the alpha 1 as a vector is just the I1th row of the generating matrix of C. Since the verifier knows the generating matrix of C, it can compute the alphas. If what I, yeah.
Just to clarify, so the generator matrix of the tensor product code is just the canonical product of the generator matrix
Of C, the generated matrix of C to the n is the outer, it's the tensor product of all the generating matrices. Okay, since I keep using this term, the generating matrix, let me just say C is a linear transformation, so it can be expressed as a matrix, and this matrix is called the generating matrix. Okay, so now that we have this sum, which is really like the sum check protocol form, let me do another step and say, okay, we assume that the code word small d is consistent with the formula phi. So we can replace here phi with d. Because phi and d just agree on all the Boolean hypercube, and here we only have coordinates that are in the Boolean hypercube, so it doesn't matter. And now we can start doing the sum check protocol. So as in the original sum check protocol, we want to strip summations one by one. So we start by defining a function g, which is, I can't use alpha now, so let's use beta. So beta, so g of beta would again just be this summation starting from the second coordinate. J2 equals 0, 1, alpha 2, J2, and Jn of d J1. Oh, sorry. Yeah, beta and J1, J2 to Jn. Actually, maybe beta is not a good notation because it's not a field element, it's a coordinate. Let's see, what was the notation I used? Okay, so let's say k. Other than beta. Okay, k1. Okay, so now the second technical claim that I'm not going to prove, but it's not hard to prove, is that G is a code word of D. Just as before G was a low degree polynomial, now it's a code word of D. Why is that? Well, for every fixed choices of J2 to Jn, it holds that D, with k being the only free variable, and J2 to Jn fixed, is a code word of D, of capital D. This is just the way I defined tensor product codes. And now what we have here is therefore a linear combination of code words of D. So in particular, it's a code word of D, because D is a linear code. So G is a linear, so G is a code word of D. So now prover sense, the prover sense G bar, which is supposed to equal G. And is a code word. Yeah, and is a code word of D. And now, the first thing that the verifier checks is that indeed alpha 1, 0 times G bar 0 plus alpha 1, 1 G bar 1 is indeed equal to U. Now, if the prover was telling the truth, then after we check that, we are done. If G bar is indeed equal to G, then after checking this, we are done. So it remains to check that G bar is indeed equal to G. And now, in order to do that, we'll proceed as before, verifier sense random R1 in L set V1 equals G bar R1 prover now needs to prove that G of R1 indeed equals V1, which is the same as saying that sigma of this exponential sum there is equal of D R1 J2 equals V1. And again, we end up with a claim, with a new claim that is just like the first claim, but with one summation less. And moreover, it has completeness. If the prover was honest and the original claim was true, then this claim will be true. And it has soundness. If D has a sufficiently large distance, then we can say that if the original claim was false, then G bar must have been different than G, but they are both code words of D, of capital D. So this means that for a random R1, they will, G bar and G will differ on R1 because they are code words of D. So this claim will be false. And now we can proceed to the next round. And and we continue to strip summations one by one until we end up with a claim of the form D R1 to Rn equals V, which has the same completeness and soundness properties. And this is exactly what we wanted to output. Mm-hmm.
Weird that you didn't need
Mm-hmm.
the fact that d to the n is large distance, in fact constant distance. This is what is supposed to motivate the whole thing, that he has, so picking a random coordinate is fine, but it necessarily follows from the error analysis here, which, because you have to, the distance in
Yeah.
pair in every copy of D has to be at most 1 over n. So this product.
Yeah, but if you look at the original proof, they also don't use the fact that
Yeah, I know. But they don't talk about codes. For you, it's, you're talking about codes and distinguishing.
right.
And so, a priori, it looks like maybe d to the n could have had an exponentially small distance, and this would work, which clearly cannot be.
Yeah,
So, but the error analysis forces it to have a large distance.
right.
D to the n.
Did it use that the code is systematic? Or?
No, I didn't use it yet. I'm going to use it in the second part. Okay, so now let's do the second part, which is revisiting the arithmetization. What can I erase? So let me see. So I will start by writing a simplified claim or a simplified lemma that is false. And we will start proving it, and we'll see where we get stuck, and then we will write the correct claim, the correct lemma. So we have the following lemma, which I refer to as generalized arithmetization. Basically, what it does is that it does arithmetization with an arbitrary tensor code. And it is false, but don't mind that. For every code D and phi, formula phi, from 0, 1 to the n to 0, 1, there exists a code word small d of capital D to the n such that one, D is consistent with phi. 2, D to the I bar is efficiently computable. That is, there is a polynomial time algorithm that is given D, the generating matrix of D, it is given phi, and it is given a coordinate I, and it computes small d at coordinate I. And I claim that, actually, let's denote it D sub phi. So I claim that this is just a generalization of the arithmetization, of the classical arithmetization technique, which works with capital D being the univariate low degree code, D to the N being multivariate low degree code. And what we get here is, and what we usually get is a polynomial P sub phi, and now we have a code word D sub phi. So now, before we prove a dilemma, or disprove the lemma, let's see how would we use it. So the thing is that once we have it, we can really prove that quanp containing IP without any polynomials. It will be in the same stage as I mentioned before. First, the verifier will take a formula that it wants to be convinced that is unsatisfiable, and it will construct D sub phi. And it also, as a thought experiment, the verifier will also keep in mind some encoding small c of the truth table of phi. And now the verifier will choose a random coordinate I bar of small c, and ask the prover to prove that small c at I bar is 0. Because if phi is unsatisfiable, small c must be the 0 code word. Then they will execute the subject protocol and obtain a claim of this form for D sub phi. D sub phi at some coordinate r equals v. And now D sub phi at r is efficiently computable, so the verifier can compute it on its own, and we are done.
So in the polynomial you showed, what is this I?
Sorry?
The original polynomial you showed, what is this I?
In the original what?
Protocol.
Oh, so in the original protocol there was no I, or I was fixed to be this, coordinate, which is the exponential sum over all assignments. And because the characteristic of the field was assumed to be large, it was okay. But actually, we could do it, we could change the original proof to work with a random coordinate, which would just be a random exponential sum of the form written here. And if we did that, we wouldn't need to use the assumption that f has large characteristic, and we could work with a much smaller field.
This generalization already doesn't work for Sharpie.
Right.
Whereas the original worked for Sharpie.
Right. Okay, so now that we...
So in this lemma, when you say that D of pi is efficiently computable, that is assuming some efficient description for phi?
yeah, phi can be just written, and assume that there is an algorithm that takes as input phi, the generating matrix of capital D, and the coordinate I, and computes D sub phi at I. Okay, so now let's prove the simplified lemma. as a warm-up, let's assume that the formula phi is read once. That is, each variable appears only one time. Assume phi is read once. So now we construct this sub phi inductively. If phi is just a single variable, then this sub phi equals the encoding via capital D of the message 0, 1, of the message 0, 1. Or actually, since the message length of D is larger than 2, probably, then we will pick some arbitrary continuation, say all zeros. No. The truth table of phi is 0, 1. Phi is a formula of one variable, and its truth table is 0, 1. So all we need is an arbitrary code word that begins with 0, 1.
The name of the coordinate does not enter it.
Does not matter.
X7 and X5 will be mapped.
Right. And here we use the fact that the code is systematic. Next, if phi is the negation of some other formula phi prime, we set this phi to be the encoding via d to the n of the all ones message minus d sub phi prime. And again, we use the fact that the code is systematic. So the Boolean hypercube of this code word will be all ones, and once we subtract from it this sub phi prime, we actually get a negation of the Boolean hypercube. No, because here we only had one variable.
So you're assuming that phi is an n variables for the sake of this?
Yeah. Yeah. Here we assume that D has n variables. Or if we would like, we can write n sub phi. Finally, we deal with the case that phi is phi 1 and phi 2. Disjunction can be dealt with using the Morgan law. And now, note that we assume that phi is read once, so those two formulas do not share variables. So actually, this formula is over n1 variables, and this formula is over n2 variables, and n equals n1 plus n2. And now this will require some explanation, and I will give it. Exactly. D sub phi would be D sub phi 1 tensor product D sub phi 2. No. So now let me remind. In general, the tensor product of two vectors, let's say W tensor product Z, is the matrix that is in coordinate ij equals Wi times Zj. And this is what we set here. So first, it's easy to see that this is indeed consistent with the formula, but I need to argue that it's a code word. So, I won't prove it, but in general, it's true that d to the n1 tensor product, d to the n2 is where actually this can be viewed both as the tensor product as I defined it before, but also as the code spanned by the tensor products of all code words here is d to the n1 plus n2. It's, again, it's an easy claim, but it's technical and I don't want to get into it. And
Could you just write out why the result is consistent though?
sorry? Oh, just because, okay, for every assignment to d sub phi, by definition, what we have here is the is the value of d sub phi 1 at the part of the assignment that belongs to phi 1 times the value of d phi 2 at the part of the assignment that belongs to phi 2. Exactly.
So why is the second step efficient?
Why with which step?
Complement.
Oh, the complement. Well, there are a few ways to do it. One way is to note that this thing is can be obtained as the tensor product of n copies of the encoding of the all ones message via d. Okay. And actually, it was a good question. So, well, this is clearly efficient. This is efficient because we can do the tensor product of n code words, each encodes the all ones message. And this is efficient by induction, because we can compute a single coordinate using this formula. So now what do we do if the formula is not read once? So now I'm going to cheat. I'm no longer going to work with the original formula. I'm going to change the formula. And the thing is that every formula phi can be transformed into a formula of the following form: phi read once and phi equalities, where this is a formula that is read once, and this formula contains only of equality constraints. And this is done just by taking every variable of phi and replacing it with some copy of it, and then adding equality constraints that checks that different copies are equal to each other. Furthermore, because we can generally assume in the satisfiability problem, every variable appears at most 3 times using similar tricks. We can assume that phi, the second formula, phi equalities, looks like x1 equals x2, x3, and x4 equals x5 equals x6, etc., where each such bunch of equality constraints contain only 3 variables and they are disjoint. Okay, so now how do we deal with this form of the formula? So first we can construct d phi read once as before. And I claim that dealing with the equalities part is easy. And the reason is Well, let's look only on a single bunch of 3 equality constraints. This is something of finite size, so we can just compute in brute force the encoding of the truth table of this via d to the third. Now, after we did that, we have conjunctions of pieces like that are over disjoint variables, so we can just take their tensor product. So this gives us d phi equalities. But we still need to combine those two somehow. And this is not easy. And to this end, we use a tool called multiplication codes. Which is a triplet of codes that satisfy the following property. For every dA in capital DA, dB in capital DB, it holds that dA times dB belongs to capital DM, is a code word of capital DM, where here the multiplication is coordinate-wise. We multiply the ith coordinate of dA by the ith coordinate of dB. And as we will see in a second, we can construct such a triplet of codes easily from an arbitrary code D. But let's see first how do we use this here. So what we will actually do is to construct this d sub phi read once for d a to the n, and to construct this one, the d phi equalities for db to the n, and finally we will set d sub phi to be d phi read once times d phi equalities. And this, and it's not stated here, but it can be shown that in this case, this belongs to d m to the n. Basically, the reason is that about this code word, we know that when we restrict all coordinates but one, we get a code word of dA. Here we know that if we restrict all coordinates but one, we get a code word of dB. So if fix all coordinates here but one, we get a product of a code word of dA and a code word of dB, so it's a code word of dm. So this whole multiplication is a code word of dm to the n.
And the only reason you use it just once, I mean that you could have used the multiplication code to encode the formula from the beginning without just.
Yeah, but
you don't want to lose in parameters there. You don't want to.
Exactly. This construction allows me to do multiplication just once, not more than once. As we will see, it is possible to extend it to have a constant number of multiplications, but not more than that.
So apart from polynomial codes, what other codes are multiplied?
We will see in a second.
So if you do this in the original setting, then you get the constant degree value.
Yeah. let's see. So just to correct what's written here. So what we will actually need to assume is that the code D is actually the code DM from the triplet of multiplication codes. And we will have to assume that phis of the form read once and qualities. This is the correct statement of this lemma. And it is sufficient, and it is still sufficient for our purposes. Okay, and this is generalized arithmetization, and all that remains is to show that the construction of the multiplication codes. So now, in order to construct those multiplication codes, take any code D from f to the k to f to the l. D to the a would be from f to the k to f to l squared, and is defined as follows. It maps a message X to an L by L matrix, all of whose rows are D of X. We just write a D of X in a matrix many L times. DB, same with respect to columns. And dm would be d squared. Now, why should this work? Why should it satisfy the multiplication property? Well, the point is that that we have the following: dA of x times dB of y is exactly d of x tensor product d of y, which belongs to d squared. And this is our construction. Now, so this is an easy construction and it works for every capital D, but the problem with this construction is that it generates multiplication codes that have a quadratic blow-up. That is, the block length, the code word length of dA is quadratic in the message length. I don't know of any construction of multiplication codes that are not polynomials and have anything that is better than quadratic blow-up.
No, they were for polynomials. The degree increases.
Sorry?
They were for polynomials. The value of the degree increases.
Well, for start, you can take Reed-Solomon univariate polynomials, and then you get quadratic, and then you get linear blow-up in the code word length. So.
If your messages come from a small set.
Why?
You go from degree D to degree 2D commonly, right?
Yeah. Okay, so I think that we should finish soon. So let me just say what are the basic ideas of going to IP. Sorry? To PSPACE, sorry. Oh, actually. So when we are talking about PSPACE, we use a different we use a PSPACE complete language, which is called the QBF, quantified Boolean formula. And this means that we have a formula of with two kinds of quantifiers: existential quantifiers and existential quantifiers. That is, we have something that looks like that. For every x1 in 0, 1, there exists x2 x2 equals 0, 1, so on and so forth. Some quantifier qn xn equals 0, 1, phi x1 then. And the PSPACE complete problem is to take such an expression as input and check whether it evaluates to true. So we need to design a protocol that allows the prover to convince the verifier that this expression evaluates to true. In the original proof, what is done is to replace, is to take this expression and to replace existential quantifiers by summations and universal quantifiers by products, and then perform the sum check protocol. But here we need to be careful, because whenever we have a universal quantifier, whenever we have a product, the degree of the polynomial is doubled. So after a few universal quantifiers, the degree blows up and becomes too high. And there are a few ways to get around it. In the original proof, there is some algebraic trick that is used to reduce the degree. Or I don't know if it was exactly the original proof, but it was in one variant of it. In our
you introduce new variables, and in these variables
exactly. There is also a different way to do it that is more algebraic. And I don't think, and does not involve, I think, new variables. But anyway, in our proof, we have a very similar issue. In order to emulate universal quantifiers, we need to use the multiplication codes. But the multiplication codes only allow one multiplication. So once we use those multiplication codes, we move from dA and dB to dm, and at this point, we are stuck with dm forever. There is nothing else we can do. So in order to solve this problem, we recall the fact that we have the general sum check protocol that allows us to move from a consistent code word to an encoding. So what we do is to know that after we use one multiplication of the expression, we get a code word of dm to the n that is consistent with the formula. And we can use the sum check protocol to move back into an encoding of the truth table of the formula via dA and dB. So we go back and forth. Whenever we have a universal quantifier, we use the multiplication codes to move from dA and dB to dm, and then we use the sum check protocol to move back to dA and dB. This is the basic idea. And this idea follows a previous paper of Guy Rothblum, Yael Kalai, and Shafi Goldwasser that did a similar idea. They didn't state it in this term, but in our terms, what they do is just whenever the universal quantifiers make the degree of the polynomial be too high, we use the sum check. Well, then at this point we have a high degree polynomial that is consistent with the formula, and we can use the sum check protocol to move back to the low degree extension of the truth table of the formula. So they reduce the degree in this way. They use a sum-check protocol to move from a slightly high degree polynomial back to the low degree extension, and they reduce the degree throughout the protocol. And so actually the generalized some version of the sum-check protocol came by trying to generalize their idea. Okay, so this is it. Thank you.